In calculus, we often need to find the volume of complex three-dimensional shapes. When a region between two curves is rotated around an axis, it creates a hollow solid. Today, we will master the washer method, specifically focusing on rotations around the vertical y-axis. This technique is essential for engineering and physics applications involving hollowed-out parts. Think of the washer method as an extension of the disk method. If the area we are rotating does not touch the axis of revolution, we end up with a hole in the middle. To calculate this volume, we take the larger solid's volume and subtract the smaller empty space inside. This difference creates the washer shape. To set up our integral, we must identify which curve is further from the y-axis. The curve furthest away is our outer radius, while the curve closer to the axis is our inner radius. Identifying these correctly is the most important step in ensuring a positive, accurate volume calculation. The area of a single washer is the area of the outer circle minus the area of the inner circle. Mathematically, this is pi times the outer radius squared, minus pi times the inner radius squared. By factoring out pi, we get our cross-sectional area formula, pi times the quantity r squared minus r squared. To find the total volume, we sum up an infinite number of these thin washers using integration. The volume of V equals the integral from c to d of pi times the difference of the squared radii. Note that the integration is with respect to the dy, meaning we are stacking these washers vertically along the y-axis. The thickness of each washer is represented by the differentials dy. Your limits of integration must be y values. If your curves intersect, solve for the y-coordinates of those intersection points. These values will be your c and d in the integral. Using x values by mistake is a frequent error, so always double-check your axis of integration. Let's try an example. We will rotate the region bounded by x equals y squared and x equals y around the y-axis. Between y equals 0 and y equals 1, the line x equals y is further from the y-axis than the parabola x equals y squared. Therefore, our outer radius r is y and our inner radius of r is y squared. Now we plug these into our formula. We have the integral from 0 to 1 of pi times the quantity y squared minus y to the fourth. Integrating y squared gives y cubed over 3, and integrating y to the fourth gives y to the fifth over 5. We then evaluate this from 0 to 1. Subtracting 1/5 from 1/3 gives us 2/15. So, the final volume of our solid is 2 pi over 15 cubic units. Visualizing the shape, it looks like a flared funnel with a curved interior wall. This result represents the exact space occupied by that solid. In our second example, let's rotate the region but the set between y equals square root of x and becomes pi times the vertical integral from 0 to the square root of 2. And x equals 2 around the y-axis. Our outer radius squared is 2 squared, which is 4. First, we rewrite the curve as x equals y squared. Our inner radius squared is y squared squared, which is y to the fourth. This setup accounts for the hole created by the parabola near the y-axis. Here, the outer radius is the constant line x equals 2, and the inner radius is the curve x equals y squared. We perform the integration to get 4y minus y to the fifth over 5. Evaluating at the square root of 2, we get 4 root 2 minus 4 root 2 over 5. This simplifies to 16 root 2 over 5 times pi. Calculations like these are common in determining the displacement of fluids in manufactured parts. Generally, if the axis of rotation is x equals h, the radius is the absolute difference between the function and h. If the axis is to the left of the region, we subtract the axis value from the function. If the axis is to the right, we subtract the function from the axis value. Consider rotating around x equals 4, which is to the right of our region. The curve furthest from x equals 4 is actually the one on the far left. So, the outer radius is for minus the leftmost curve, and the inner radius is for minus the rightmost curve. Order is everything when the axis shifts. Sometimes curves cross within the interval of integration. In this case, the inner and outer function swap roles. To solve this, you must split the volume into two separate integrals, recalculating the radii for each section to ensure you are always subtracting the smaller volume from the larger one. Another frequent error is squaring the difference of the radii rather than the difference of the squares. Remember, we are subtracting the area of the small circle from the area of the large circle. Pi times r minus r squared is not the same as pi times r squared minus r squared. Don't fall for this algebraic trap. Finally, watch your bounds. It is easy to accidentally use the x-intercepts as your limits of integration because they are often the first numbers you find. Always look at the vertical span of the shaded region to identify the correct c and d values for your dy integral. Let's summarize. To find the volume of revolution around the y-axis using washers, first, ensure all functions are in terms of y. Second, find your y limits. Third, identify your outer and inner radii by looking at the distance from the axis. Finally, plug them into the integral formula and solve. The washer method is a powerful tool because it handles hollow objects with ease. By subtracting the empty inner volume from the full outer volume, we can describe complex 3D geometry with a single, elegant calculus expression. Mastery of this formula is a stepping stone to multivariable calculus. Before we go, here is a quick question. If we rotate the region between x equals y and x equals the square root of y around the y-axis, which function is the outer radius r? Look closely at the interval between 0 and 1 to see which curve is further to the right. The correct answer is B, the square root of y. In the interval from 0 to 1, the square root of a fraction is larger than the fraction itself, placing it further from the y-axis. Great job today! You are now ready to tackle volumes of revolution generated by Vision Solve AI.